In today's lecture, I am going to talk about the first law of thermodynamics and some special cases related with the first law of thermodynamics, like adiabatic process, constant volume process, closed cycle process, and free expansion. This is the topic 18.10 and 11 of the Fundamentals of Physics book by Halliday Resnick Walker. From our previous discussions, we know that whenever a system undergoes a change from some initial state into some final state, then the properties like work done and heat depend upon the nature of that process. In our previous lecture related to PV diagrams, we have seen many of such situations. This makes it certain that the quantity heat Q and W depends upon the nature of process. But however, one thing is for sure, that the quantity Q minus W remains constant in all the process. This quantity Q minus W depends upon the initial state and final state of the process, and it doesn't depend upon the any intermediate stages. So whatever the system undergoes between initial and final stages, it doesn't depend upon them. It only depends upon the initial and the final state. This is only true for Q minus W. Quantities such as Q alone, heat alone, or work done alone, or Q minus 2W or Q plus 2W, any of these quantities doesn't remain constant. It is only property of this Q minus W. So all of these terms are path dependent, right? Whereas Q minus W is path independent, one can say that. So this also suggests that Q minus W should be equal to some intrinsic property of the system, and we call this intrinsic property as internal energy of the system. Now we need to look at the internal energy. What is internal energy? Internal energy is basically energy associated with random and disordered motion of molecules. However, one thing should be considered, that this internal energy is at a microscopic level, not at a macroscopic level like the motion of heavenly objects. So our first law of thermodynamics could be written in equation form as that internal energy, which is a state variable. State variable are those which depend upon the initial and final state for their representation, which would be internal energy final minus internal energy initial should be equals to heat minus the work done. By looking at this, one can say that internal energy of the system increases when this quantity heat, when Q or heat is added to the system, right? And this internal energy decreases when energy is lost as work done by the system. Okay, and looking at this equation, let me call this as equation A. This internal energy of the system will increase if heat is added to the system, and it will decrease when this W actually increases, right? And W increases when work is done by the system. This will decrease the internal energy of the system, right? In this case, however, considering the first law of thermodynamics, we are taking the change in kinetic energy or change in potential energy of the system to be 0. There are two types of work done. One type of work done is that we are taking work done by the system, and the other type of work done is work done on the system. And work done by the system is always equals to negative of work done on the system. So we can modify equation A that represents our first law of thermodynamics as internal energy is equals to Q plus work done on the system. Now, considering this work done on the system, internal energy increases when heat is added to system or work is done on the system, and this internal energy will decrease when heat is lost from the system or work done on the system is negative, that is work done by the system. This delta E internal will increase when heat is added to the system or work is done on the system, and this internal energy of the system will decrease when heat is lost or work done on the system is negative, and this work done on the system is negative means work is done by the system. Let me call this above equation as equation B. So in summary, one can say that internal energy of the system increases when heat is added to the system or work is done on the system, and internal energy of the system decreases when heat is removed from the system or work is done by the system. One can also say that when heat is added to the system, Q is positive, and when heat is removed from the system, Q is negative. When work is done on the system, it is taken as positive, and when work is done by the system that we are representing by W, that is taken as then work is done by the system that on the system would become negative. So this is our first law of thermodynamics, which is basically a relationship between internal energy of the system, amount of heat added or removed from the system, and the work done by the system or on the system. Now let us look into the second part of our discussion, that is some special cases related with first law of thermodynamics. The first case that I am going to consider is adiabatic process. The adiabatic process are those processes in which are very rapid, or the containers are insulated, or the equipment or system is insulated in such a way that there is no heat transfer, no transfer of heat into or out of the system. I am first writing down the first law of thermodynamics, that is internal energy is equals to amount of heat minus work done. Now when there is no transfer of heat in and out of the system, this means Q is equals to 0, right? This amount of heat added or removed from the system is 0. Now put this in equation A. You will get internal energy is equals to negative of the work done. Let's say this is equation C. One can say that in this case internal energy of the system increases or decreases at the expense of the work done. Now this internal energy would increase when this W is negative, right? And this W is negative when work is done on the system, right? W is negative when work is done on the system, increases when work done on the system. And this internal energy would decrease when work is done by the system. So in discussion of adiabatic process, you can write internal energy is equals to minus W is equals to work done on the system. This was my equation C. We can realize this relationship by taking a container right? Gas is filled in it like this, and this container is properly insulated. You can take the example of a thermos like this one, and there is a lead shot. This is a lead shot that is placed on it, that can be moved up or down. Now one can see in this figure that it is properly insulated. No heat can enter the system or it can leave the system. However, the work could be done by moving this lead shot up and down. Let's suppose work can be done by the movement of this lead shot. Suppose if the lead shot moves above, then the gas in this container will basically expand, and work will be done by the system. So when there is work done by the system, the internal energy of the system will decrease. On contrary, we can say that when this lead shot is further compressed or moved downward, the gas inside that insulated container will be compressed, and this will be the work done on the system. So internal energy of the system will increase. This proves our point that whenever in case of an adiabatic process, whenever there is work done on the system, the internal energy will increase, and whenever the work is done by the system, the internal energy of the system will decrease. You can take an example. Suppose if a person is not eating from a couple of days, or say for quite some time, then he or she is basically burning his or her fats, and you can say that fats or proteins are internal energy of the system. So the internal energy will decrease as no food is entering the system. But the case of the food is at a macroscopic level, and we are discussing thermodynamics process which are at a microscopic level. However, we can relate the similarities between them. Next case is this was case 1. Next case is constant volume processes. In constant volume process, you can basically change the volume of the system. Let's say if this lead shot is fixed in this case, then you cannot change the volume of the system. This will bring down the work done to zero. There will be no work done on the system or by the system in case of a constant volume process. So our equation A, that is first law of thermodynamics, that is internal energy is equals to the amount of heat minus work done, would be equals to delta E internal is equals to the amount of heat. Let me call this as equation D. Now this equation D clearly states that internal energy of the system would increase when heat is added to the system, right, or when Q is positive, and this internal energy of the system will decrease when Q is lost or heat is removed from the system or Q is negative. In this scenario, you can take the example of a pressure cooker. Once we close the lid of that pressure cooker, and when we basically give heat to it, then the internal energy inside that pressure cooker will increase as we are adding heat. But there is as the volume is not changing of the pressure cooker, so work done would be zero. And when basically you take the heat out of it, and basically you remove the lid, then steam comes out. It means heat is being lost to the system, so internal energy would be decrease in this case. You can relate basically cooking of food in a pressure cooker to the constant volume process. Next special case that I am going to discuss is third one is cyclic process. Cyclic processes are those processes in which you start from a point and after passing through the some stages, you come back at the same point. So your initial and the final state remains the same in this case. This property of this system will basically result in change in internal energy of the system to be equal to zero. There would be no change in internal energy of the system when a system comes back to the same point from where it started. However, the amount of heat can change from stages, or work done may change. And putting this in equation A of first law of thermodynamics will result in 0, that is internal energy is equals to Q minus W, and this amount of heat would be equals to the work done, and this is, let's say, my equation E. This equation E suggests that the net work done in this case would be equals to the amount of heat that is added to the system. As much as you add the heat to the system, more and more net work will be done by the system. In my previous lecture, I made a PV diagram . This is, let's say, my initial point. This is some final point, and let's say if it comes back to the initial point, this represents a cyclic process in terms of a PV diagram. Similarly, constant volume process in terms of PV diagram would be constant volume process. Let's say this is volume and this is pressure. All these vertical lines, right, will represent basically a constant volume process. Now the last special case in terms of first law of thermodynamics is free expansion. There are some thermodynamic processes in which there is no heat enters or leaves the system, and there is no work done by the system or on the system. This leaves Q and W is equals to 0. Now putting these values in equation A of first law of thermodynamics will result in internal energy of the system to be equal to 0. Such processes basically represent free expansion. This free expansion can be explained with the help of a diagram. let's say there is a gas confined, there is a two chamber system and gas is confined. This is my chamber 1, and let's say this is my chamber 2. Chamber 2. Gas is confined in chamber 1 and it fills the volume of the container, and there is a stopcock placed in the path between this chamber 1 and chamber 2. Now as this stopcock is closed, the gas is confined in chamber 1. Now these chambers are properly insulated so that no heat can enter or leave these chambers. When you will basically remove this stopcock, the gas will stop expanding and it will also fill this chamber 2. Now since there is no heat energy transferred into or out of the system, and similarly there is no work done in this case, so one can say that the internal energy of the system, change in internal energy of the system remains 0. This also means that no work done by the gas because it rushes into a vacuum, and thus does not mean any change in pressure. So this sums up our discussion of today's topic. First we discussed the first law of thermodynamics, that internal energy of the system is equals to the amount of heat minus the work done. Then we studied some special cases like adiabatic process, constant volume process, cyclic process, and free expansion. Now hopefully you have understand this lecture. In next lecture I am going to be discussing the heat transfer mechanisms like conduction, convection, and radiation. Thank you all.